me when 15, 20 years ago. Well, 15 years, yeah. Good to let me go. So,
yeah. Okay. So I hope it's all good now.
yeah, good. Yeah.
Perfect. Perfect. Okay. So let me start there. Yeah. Thanks, Andrew, for the kind introduction, and thanks for the organizers for putting together this nice program and the opportunity to present some of our recent results here. So my talk is roughly split into two parts. In the first part, I want to discuss a little bit about how we can use current quantum computers for simulating topological order. And in the second part, I want to discuss some new view on topological orders using higher form symmetries, which we can then use to understand what we possibly see in these phases. So in the first part, I basically want to talk on topological phases of matter, and these can be overall very rich and complicated, as for example in quantum spin liquids or various materials. So there's a lot of exciting structure. However, that makes it also extremely complicated to understand these cases and moreover to actually realize it. So what I basically want to look is I want to look at some sort of stripped down version of topologically ordered system, make it as simple as possible so that we still have something non-trivial to look at. And then I want to show that using these kind of stripped down versions, we can then actually put it on current hardware and actually kind of see some of the hallmarks of topological phases of matter. So I think this one introductory slide I can probably keep extremely short. So that there are now some examples already known in condensed matter where these exotic phases actually have been realized and understood extremely well. And then on the theory side, there are now various proposals for model systems that realize topologically ordered quantum spin liquids, but the experiments are a little bit behind. So there are no very concrete examples where there's some smoking gun experiment. At least this is my claim at this moment. And then there are also more exotic phases where symmetries still play a role, and then the interplay between symmetries and quantum fluctuation leads to some so-called symmetry-protected topological phases. Sure.
So symmetry-protected topological phases like AKLT is long-range entanglement. Is that how it?
Right. Good point. I mean, so what you have in these symmetry-protected topological phases is some sort of symmetry-protected entanglement. So for example, if you take the AKLT chain and you want to disentangle it, then you can't do it, assuming that you have certain symmetries in the system. So
you can do it in the short circuit if you break symmetry.
Is that right? Yeah. In this way, I mean, I agree. Putting long-range entanglement is maybe a bit misleading because in these cases you do have symmetry, you do have entanglement which can be removed by finite depth circuits if you just don't play by the rules. So let me just exactly. I'm about to just hide it all the way. Good. Right, and what I now want to talk in the first part is basically that I want to discuss how we can use quantum processors or quantum computers actually as a platform for realizing representatives of these topological phases. So that we are not trying to find a specific material, but we just design these phases on a quantum computer. So now coming down to the stripped down, very simple model which realizes topological order. And this is now the toric code model, where we have like the physical degrees of freedom living on the bonds of a square lattice as shown here. And for the interaction in the Hamiltonian, we have now a vertex term, which is now the product over all sigma z's around a given vertex. And we have the plaquette term, which is now the product of sigma x's around a given plaquette as shown here. So now, again, I assume that this model is known to most of you. There's a nice property that that all terms in the Hamiltonian commute. So we can now find, we can diagonalize it by diagonalizing these terms individually. And then we find that the ground state of this model is simply an equated superposition of all loop coverings of the lattice, right? So the way that I'm thinking about these loops is that I'm now going here to the sigma z basis. So I have now the representation of the spin, where I say that, well, whenever the spin is in the +1 state, I leave this bond empty, and if the state is in the -1 state, I put here like a red bar. And now I would find that if I just construct a state which is an equated superposition of all loop coverings of the lattice, then that is the ground state, and the ground state then has Z2 topological order, and moreover, yes.
Very basic question. By loop coverings, you mean non-intersecting loops? Or
No, also I didn't draw it here, but also intersecting loops. So basically, where this constraint is coming from is from the vertex term, which is now the product of the sigma z's. So I want to have an even parity. So all spins up or all spins down is also good. So I'm allowing for intersections. If I were to take the superposition of all non-intersecting loops, or all kind of, or if I would take the fully packed loop covering with non-intersecting loops, then this would be a critical state. Good, thanks. Good. So now we have, so now we have this. This is the ground state, and one of the exciting properties of the state is that we can now create excitation. So we can now break open some of these loops, and then we have now these point-like excitations at the end of open strings, and these strings are anyonic excitations. I'm going to say a bit more what I mean by this in a moment. So now we can come to the first task, right? So now we have a very well-defined state, namely the state which is the equated superposition of all loop coverings, and now we can say that, well, now let us assume that, well, it would be, in this case, we do have access to a quantum computer that can do certain elementary operations, and how can we then prepare the state in an efficient way, right? So basically, this is the task. So the building blocks are now unitary two-side gates, and how can we now write a program running on a quantum computer to prepare this particular ground state? And this I want to explain here. So first of all, I'm switching now to a slightly different representation. So previously, I was showing this black lattice, so this black square lattice which you see here. So and then we have the degrees of freedom on the bonds. So here these are now the qubits or the Ising-spin degrees of freedom that we have. And now I'm just leaving out this lattice in the following. So here now on the sides of this rotated square lattice, we have now the qubits. So now I can initiate the quantum computer into a state which is just simply a product state of all states being in the zero state. If I'm taking this product state, like this product state of zeros, this is already the ground state for all vertex terms, and this is now in this kind of drawing indicated by having a blue shade of this plaquette, right? So basically, what I do by taking these plaquettes, which correspond to the vertices, I color them now blue for them being in a parity even state, so which means this is the ground state of the plaquette term with the of the vertex term, and I would color them red if they're in the excited state. So now we see it's in the ground state for all vertex terms, but it's in the zero energy state for the plaquette terms. So now we can just we propose the sequence of operations that we can now apply sequentially. So first we apply Hadamard gates to a subset of the qubits, which means the Hadamard takes now the zero state into a state which is 0 plus 1. And now we see that by applying this Hadamard gates, we're actually destroying the state for the vertex terms, because now the vertex terms that were happy, they were dark blue, now turn to gray, which means that they're in a zero state. Now what we do is we sequentially, like a zipper, from the inside to the outside, apply these control Z gates, which are shown here. Right? So depending on the state of this qubit, we just perform a flip here or not. And if we are now sequentially applying these C0 gates in the way as shown here from the inside to the outside, then once we are done with this algorithm or with this sequence, then we are in a state where now both all the vertex terms and all the plaquette terms are in the ground state. So we have then actually now created the ground state of the toric code Hamiltonian. And this construction now requires a depth which is linear in the system width. And in fact, one can show that this is a minimal width depth that you need. So you can't have anything that's linear and scaling faster. That's unitary and scaling faster.
Can I just ask
Sure.
about the boundary conditions? So I guess it's just a finite system. And,
Yes.
I mean, regardless of how you define or how you prepare your edges, either the BP or the A, what is it, it can't be defined
or
on
V
the
or
edge.
P,
I
yeah.
mean, one of them always
Uh-huh.
is incomplete. So how is this dealt with?
Oh, here we choose such a termination that there is actually unique ground state. So basically, you just have then partial plaquettes here on which you require this constraint.
Mhm.
Right. So here, for example, we have now a plaquette term at the edge where we still put them into a state. So here's like a partial plaquette, and it's still like the product of these here has to be plus
Yeah,
one.
but if you have the plaquette terminating, then there is no bond coming out.
That's right. Yeah. So this is called the smooth edge, where we would not have degeneracy. But indeed, you can also just choose other boundaries where you would then find a very large degeneracy. Yeah.
How can you be sure by the time you put your zipper out to the edge of your sample that you haven't decoded it in the middle?
Yes. Oh, because we can. I don't have this measure. So basically, what we can do is we can now prepare the state, and now we can just do measurements. So we can just basically first prepare the state, and then we just do these measurements. And this is exactly also what is basically shown here in this coloring. So we have now our algorithm that is creating these which is creating this state, and then we can now So then we can.
So can you measure the A's and the B's?
Yes, that's right. Exactly. Because these are stabilizers, so they commute, so we can just measuring them all simultaneously.
So you can do that in practice, not just in theory.
This is done on the quantum computer. Yes. Yeah. I can actually quickly open up another presentation. I can show actually the result real quick.
How do you actually measure the A's and the B's without screwing things up?
1 second. Let me just quickly see if I have a talk where. Yeah. Actually, this is measurement already. So there are different ways. So one is of course that we can run this code many times, and we can first measure in a Z base, and then we can measure in an X base.
Okay. Yes.
And this is what's done in practice. But you can also now rotate the system. I mean, this is actually what we did. So basically, just run it multiple times, and then just sample it for the X and the Z plaquette, because then it's very easy to measure, because you just can directly measure the you just need to measure the bit strings, and from this you can read off the result. But you can also
you don't care whether you screw up the state after the measure that.
That's right. But you can also, because there is a basis in which all of those are diagonal, but that would require some other depth circuit that we would apply, which makes it harder.
Thank you.
No, that's it.
Yes.
So could you explain again how this kind of CGAs, you get these loops in the glass, you get a superposition of these loops?
Yes. So I don't know what. So basically, if you think of this state, this is basically the state that you have, right? So basically, you start with the 0 state, and now you just take the product of all 1 plus the plaquette flip term. And this would basically correspond to all those states which can be represented in terms of these loop coverings. So now the way that we just construct it is that we just fine tune in such a way. So say that here we have now for this qubit is now the up-down state, and now basically if you just apply to this specific one this control X operation, then you see that this one here that used to be in a 0 state is then also in an entangled state with the state. So basically, if this one is up, then the other one is also up. And if this one is down, then this is down. And then basically, the way that we design the sequence is such that exactly you just get this loop covering constraint, and you get equal superposition of all of them. So basically, this was there is and this is the history of this project. So first of all, we just came up with a solution to the problem in the way that we just start from the state, where we just know that this state can be written in what's called an isometric tensor network, and that we can directly translate it into a circuit that works. But then basically we look deeper into it, and then heuristically we found this one was actually more efficient. But I can give you a very systematic way of finding it. This is basically by just figuring out on a small lattice what we have to do to get these specific states, and then we just scale it up to the large one.
And this can't be viewed as an isometric tensor network in a different canonical form, perhaps.
Yeah, exactly. So maybe one can even see it a bit like this, that we just. I actually haven't tried to reinterpret this as an isometric tensor network, because you just get these kind of sequence. So it's not like this isometric tensor network would be just literally just a sequential circuit. We start maybe at the lower right corner, and then we just zip it up. Here we just act on spins different number of times in a sequential way. So it's, I mean, for sure we can write it.
Looks like an MPO that way and then an MPO that way.
Yes, exactly. So it's
it is a sequential circuit.
That's right. Yeah.
Marathon.
Yes.
Is there any particular reason you don't use measurements here?
Good point. Yeah, actually, I'm commenting on this later. So I was pointing out that this is the optimal circuit if you only apply unitary gates. But indeed, if you're just allowing for measurements, you can shortcut and you can actually just get it in a constant depth. And I'm commenting on this in a moment. The problem is that the machine that we're using at that time didn't offer this option. So, but I'm coming back to this later. Good, right? So what we now have is this. So just could you repeat? So now what we basically have is like we have now an algorithm that allows us to prepare then the ground state of the toric code Hamiltonian. So now let me just quickly see. So now that we have the ground state, we can look for different hallmarks of topological order, right? So then one, of course, is that we're just measuring the stabilizer and show that we're actually realizing the ground state, but that might not necessarily tell us that the state actually has the expected long-range entanglement or this non-local entanglement. In order to address this, we are now directly measuring the entanglement entropy, or like the topological entanglement entropy. In particular, for topologically ordered systems, we expect that when scaling the so if we just now take our system and we cut out some area, then we expect that to leading order that we have an area law. So the entanglement entropy will will scale proportionally to the length of the cut. But then there is a subleading order 1 correction, which for the toric code model is log 2, or in particular it's log 2 for the entire Z2 topological order. So, and now, having prepared the ground state on the quantum computer, we can now directly measure the entanglement entropy. And for small enough systems, for small enough blocks that we cut out of our ground state, this can be done using a full state tomography. So we can basically sample or just directly measure the reduced density matrix. And for larger ones, we use what's called a randomized compiling or randomized measurements for sampling the Renyi entropies. And in both cases, actually doing the measurements of the entropies is still exponentially hard, but for small enough subsystems, this can actually be done in practice. And the upshot is that then the measured topological entanglement entropy, which we get from adding and subtracting different subregions, is actually close to log 2 as expected. Yes?
How big a patch does this persist on? Does it take, does this signature decay as the patch gets bigger? That's quite aside from sampling.
I think that for me, it's hard to make a difference. So if you look at the data, you see that actually as we're making the patch larger, the result is getting better.
Yeah.
However, just by the way that we are constructing it, we know that there are some sort of what I could call kind of non-local errors, right? So we have this sequential generation of the state. Or let me just maybe go back a little bit. So this is now showing also like a weakness of this kind of construction, because let's say we're actually having a Hamiltonian that exhibits Z2 topological order. Even if we kind of detune now from the toric code state, we expect that this topological entanglement entropy will be robust, right? Because basically we have then the way that we can think about that, we have this toric code ground state, and then we just have local fluctuations on top of it. So basically we can think of some virtual anionic excitations, but they will just be short-ranged. And if I now basically, in that case, I would say that, well, if I just make my region larger and larger, eventually it will just converge to this log 2. Now, when we are just doing this sequential generation of the state, we don't have a Hamiltonian that actually, or there's no gap above a state which protects us. So basically, if we just do this sequential operation and we're just making some mistake or some detuning on the way, then we will create a certain finite probability of having a defect, and this will now propagate to the system. And that means that whenever I'm having an imperfect state creation, and I were able to calculate the entanglement entropy for a large region, I would find that at a certain size, this correction will actually disappear. It's actually related to what you see for a tensor network representation. If you take a tensor network representation of a toric code, for example, and you just add some noise to it, then it also disappears because you are violating this this kind of locality constraint. Yes.
So the defects which are the anionics, how would they propagate?
Well, the way you can see this in this construction. So let's say here, this is correct if every gate works exactly the same way as it should. But now let's say that this Hadamard gate maybe is not creating a perfect up plus down, but up plus down, but with a slightly shifted weight. Then you would find that the state here doesn't have the perfect equal weight superposition as it should be. And now this will actually propagate as you just apply the control X gates.
So this propagates
Yeah.
ballistically.
That's right. Oh yeah, right, it's ballistically. Good. So, but yes.
So what are the subleading terms? Because for L equals 2 or 3, is there a guarantee that these are smaller than log 2?
No, I can't tell. I mean, the thing is that in this machine, and even we had this discussion with people from Google, then I mean, even they couldn't really tell what is actually a precise size of the errors, because you get measurement errors, you get different gate errors in it. So this is a combination of all these errors. So I can't make it very confident.
No, I just mean in the sort of entanglement entropy formula.
Oh, if you just, so you ask me about the next subleading, there are some log corrections, I think, next. Not the fixed point wave function, but if you were to detune from the fixed point. So yeah, but in the toric code, there's no correction. In the toric code, this is exact.
Yeah, so that's the one thing I wanted to ask. I think it's also related. You use the subtraction scheme that is Vitale Pressing,
Yes.
which I never cross-checked. The level and when subtraction cancels all the zero terms, or or the one terms that are non-topological because of the subtraction scheme.
Yes.
So that one works even for 3. Like so long as you can do a loop, but it's a bit more complicated. Do you know if the Vitale Pressing does the same cancellation? Because in principle, there is a corner in the middle that could give over one contribution to topological, and they're not obviously subtracted, but I also never actually checked the current back. Yeah, they both work out that, yeah, but the Levin one is beautiful because it actually cancels exactly even small scale.
True. So this is a good point. We didn't, I mean, what we are aiming for to have something where we can just get the smallest possible cluster, which was for this one.
Yeah.
But this is a good point. I mean, maybe one could.
Yeah, so
directly compare exactly
the downside, but then the cancellation is exactly.
Exactly, but for I mean, these clusters are probably large enough to get to the regime.
Yeah,
so
the data show that you get it.
No, but for this construction, that for this geometry that we have, we can actually get a hole in the middle. So
be something.
Yeah. But this we haven't done. This is a good idea. Good. That's so. But the cheerful note, or what made us happy, is that we see actually that over a certain length scale, we actually do get this expected long range entanglement. It just tells us that there is actually some amount of non-local entanglement in the wave function that we created. So in the second bit that I already mentioned are the anionic excitations. So basically we can now think of the toric code state as a vacuum now, and on top of this vacuum we can create excitations, and now we can look at the one hand at the self statistics. So we just take now 2 of these excitations, we exchange them, or we just take now one type of excitation and move it around another. And in these cases, we can now measure the phases that we pick up, and these are contained in the U matrix for the self statistics and for the S matrix for the mutual statistics. So now, going to the toric code fixed point, this is all again extremely easily done. So basically now what we're looking is actually real data. So now what we can do is we can use this algorithm to prepare the toric code ground state. And now on top of this ground state, we can now create the different types of anyons. This type is like an E particle and an M particle. And we now get these states by sequentially, like by just acting on the ground state with some string operators as shown here. So for example, a string of X's is creating an E excitation, and a string of Z's is creating an M excitation. And now, once we have created this state, we can now move these particles by sequentially acting on this with, for example, X operators. And again, this is now the data taking on the machine. So we see that if we just apply these X operators, we're actually moving the excitations. The excitation now showing up as plaquettes or vertices with the wrong sign. And we see that the background is hardly changing. So there's a little bit of flickering in the background, but overall, the state remains intact.
Then does that mean the anion is not propagating? I mean, if you're making errors in these gates, and the anion, and this is the experiment.
Yes.
So the anion somehow stays spin.
I'm not fully sure. So the errors are very small. So basically, this starting state, like these errors that I was pointing out before, they're already contained in the starting state. So because like the gates are not perfectly tuned, so you will have a finite. Right. So let's put it like this: if you basically calculate the expectation value of an E operator, it should be, or the expectation value of the plaquette operator should be 0, or it should be minus, or it should be +1 everywhere. But by looking at actually grounded, there's a finite probability, but this is very small. It's at the order of a few percent.
these images are outcome of many, many shots.
Yes, that's right.
Yeah. So I suspect what happens is occasionally you get an E or an M somewhere else.
Exactly. Yeah,
But
not true. If you
average, that is a finding different shade of blue.
yeah, exactly.
This is fair. I think.
This is exactly correct. So basically, you just measure these bit strings, and then you see that these bit strings almost always correspond to a correct state.
I guess.
That's the second.
I didn't.
Well, hopefully your laptop will survive the.
Well, it's not even connected to power, so that's good. But the projector doesn't show much at the moment. Or do I have to? It's connected to HDMI, so that's
Oh, it's coming.
it's coming. Hmm.
Like take the HDMI out and put it back in.
Oh no, something is happening.
There it is.
Good. Okay, we get this movie once more. But now, yes.
So can I so if you rate anti-clockwise, you should get some place into the I theta. If you rate the other way, you should get into the minus I theta. But the string operator that rates one positive particle around the other seems to be reversible.
Yeah, but in this case, the phases that we get are at most plus or minus one.
Okay.
So then it doesn't matter.
Okay.
This is in the nature of this. But the data that we've taken here really is done basically for creating this movie, because whenever we just look at it, like if we just peek at an intermediate state, that collapses the wave function and it destroys the state. So from this experiment, we cannot extract the phase that we're interested in. But now we can perform a trick, so using a so-called Hadamard test. And now what we are doing is we are now adding one extra qubit to our system, the one here at the top corner, and now we are just creating a state where we have now the initial state as shown here, where we just now created some pairs of anyons, and this additional qubit we put into a state which is the up plus down state. So we just apply a Hadamard to this additional qubit, and after preparing this initial state, so we have now the up plus down state on our extra qubit, and we have now the ground state of the toric code with some excitations created on it. So now we just get the superposition of 0 times this state plus 1 times this state. And now what we're doing is we are just applying a controlled exchange operation. So basically we have now 2 of these copies. In one copy, we are doing this exchange of the anyons, and the other, we just leaving them at rest. And then it's easy to show, if you're then doing measuring the real and imaginary part of this extra qubit, you can then measure the phase that you get by doing the exchange or by moving one around the other. And this we done then on the machine, and the results are shown here. Let me just.
Sorry, that green cross, is that like the qubit is like a perturbation to the.
Well, you have to think of there's a chip, in this case, the Sycamore chip, and that one has the order of 50 or so qubits that you can play with. And here we're using only a subset of the qubits for generating the state. And then we just pick just another one qubit, which we didn't use for the state preparation and to this point.
Right, thank you.
Mm-hmm. So, and now from these Hadamard test measurements, we can then extract the phase vectors for all sorts of different processes that we could think of. So now just to pick some example, we could now take a bound state of an E and an M particle and exchange them. And we know that this should be a fermion. And indeed, we see that the phase extracted is near pi. If we exchange 2 E or 2 M particles, they are boson, and we just should pick up a phase of 0, and this is indeed what we are picking up here. Good. So basically now at least we found that for the simplest possible case, we can actually simulate something which we already know on the quantum computer. And let me just now briefly comment on where to move from there. So we could also then show that this kind of construction that we had, basically just using this kind of zipper construction, we can actually generalize to all stringnet models, which means that we can also realize non-abelian models for this. We can also just create the ground states of non-abelian stringnet models, and then also have operators which perform the exchange. So it's everything that we showed in the first part for the toric code model also works for more exotic models. And then there was a question already about it, but then we can actually also think about shortcuts. And this is actually quite useful for these non-abelian models, because in the circuits that we found for non-abelian models, they do scale also linearly, but the depth is much larger, so it's beyond what would be doable on current quantum computers in a meaningful way. So then there's like a shortcut. The shortcut was already discussed a long time ago by Kitaev. And the idea is now the following. One can say that, well, one prepares the state just in a simple plus state, which means like we just take the initial state as we had it before. We apply Hadamard gates now to all qubits. And now all of these states are in a plus state, which would mean that all the Plaquette terms are happy and all the star terms, for example, are unhappy. And now we would do a measurement of these stabilizers, and then we would find that certain star terms are then unhappy, so there's a problem. So and others are good. So this would roughly happen with a probability of 50% that they're happy or unhappy. But now we did this measurement and we just know exactly where the defects are. But then we also can find out classically the simple way how to fix these. And since all these X operators commute, we can then actually remove all the defects. And this is now a depth 1 circuit. So basically all we have to do is we just prepare this initial state. We just do this round of measurement, and all these states can be measured simultaneously. And then we just have to apply some Pauli X operators to fix the errors. And what was figured out in this paper by Iqbal and others is that they could just recycle this idea to actually got non-abelian anyons. And that's actually quite a non-trivial step, because this idea that I proposed here, or that I demonstrated for the toric code, it's so easy because this cleanup step only involves commuting operators, so you could just do this in one shot. If you were to do this naively on a stringnet model with non-abelian anyons, you just do these stabilizer measurements, and then the cleanup step would again be of linear depth, because then you would have to move around these non-abelian anyons, which would be hard. And then basically what they found is that in certain cases, you can now prepare a state, and you can only have to fix on a subset of anyons of that particular model, which are all abelian, and then you can just get ground states of these non-abelian models. And then they just did this on a Honeywell machine, and they in a similar way also just doing this Hadamard test, and then they could demonstrate that there are actually non-abelian anyons. Good. So this was for the part of just this the toric code ground state order. And now we thought about going a bit beyond it and think about sort of symmetry enriched topological phases. So previously we symmetries didn't play any role, and now we are saying that, well, now we take a system where we would, for example, have a toric code ground state, but now in addition we have certain symmetries. And what can happen, or what yes?
I mean, connected to the previous part, can one get fermions like this? Actual, I mean in 2D.
Yeah, I mean, these are fermions. So if I just take a molecule of an E and an N particle, this is an emergent fermion.
that asks about dynamics of those fermions?
Sure, I mean, we could now, right, so because here everything is basically static, but now if you at the level would just now introduce some dynamics that would, for example, be a hopping of a pair of these molecules of E and M particles, then this would. Yeah. So let me now quickly address the second part where I want now to include some additional symmetries. Right? So the point was that for this toric code order or for topological order in general, the Hamiltonian doesn't need any symmetries in the system. But now what I want to do is I want to add an additional symmetry. And what we can then have are now that the topological phases, like the phase, like for example, the Z2 topologically ordered phase, can now split into different phases, which have some sort of, kind of substructure. And one construction that we use to achieve this is actually to have now a toric code model represented in terms of tensor networks. And let me just very quickly go over it. And this is actually very much connected to an earlier work by Claudio. But what Claudio basically showed is that you can now have a specific fine-tuned Hamiltonian such that the ground state is actually right. So if you have a fine-tuned Hamiltonian which actually interpolates between the toric code ground state and a simple paramagnet, and then along this entire path there's an exact tensor network state which has just a one-dimension too. And what we basically now done in a similar fashion is to say that, well, now we can also write down a tensor network state which actually now interpolates between a symmetry enriched toric code and a trivial toric code. And so the way that it works, and I don't want to go into a lot of details here, is basically just that we now think of the toric code as being made out of some sort of decorated loops. Previously, we said that, well, if we have a loop in this toric code, that just corresponds to the spin up or a spin down. But now we can say that, well, we just have some decorated loop, meaning that if there is a loop, this loop can have some additional degrees of freedom. So for example, you could think of the loops being made out of AKLT chains, for example, and then you just get now some soup of AKLT chains, and that indeed has then these symmetry-enriched topological properties. And the last sentence about this is now, because previously we said that, well, we can think of the anyons as being excitations of open strings. And if you now visually think of the loops being made out of AKLT chains, then you would see that each of these anyons also carries a half-integer degree of freedom, half-integer spin, and that's actually the property then of the SET, that basically in the symmetry-enriched topological phase, the anyons transform non-trivially under a symmetry, and in the trivial toric code, the anyons would transform trivially under the symmetries. Yes?
The statistics is the same?
The statistic would be the same. The statistical property are not affected by it, but it would just be basically whether they are carrying, like for example, if you just have, as in this case also, you have a symmetry-enriched topological phase protected by time reversal symmetry, then you would just find that the anyons have a Kramer's doublet or not. Yes?
Can you tell us about the critical, like the critical point there? I mean, does it have unusual properties?
But this is a sort of an O2 loop gas. It's a critical point that you would also find in a 2D classical model.
So it's pretty standard.
That's pretty standard.
I wasn't sure whether there were any exotic.
No.
Things.
Right. So basically here, what we found is that there's now a state which is kind of simply represented in terms of, or basically the entire phase diagram here can now be simply expressed in terms of a tensor network state. But this is not enough if we want to simulate on a quantum computer. In a way, tensor networks are more computational, more powerful than quantum computers. So So now basically not every 2D tensor network state that's easy to write down can actually be simply prepared by a quantum circuit. But if we are now taking a subclass of these two-dimensional tensor networks, so-called isometric tensor networks, which means that if we take now the tensors that made up our state, and they fulfill this sort of isometry condition, meaning that if I taking the tensors and I'm contracting them in a certain way, that this gives us an identity. Basically, then these matrices, these tensors T are then isometries. Then every so-called isometric tensor network then can be expressed in terms of the sequential circuit. This is also what I replied to Andrew's question, that if we have an isometric tensor network, then we can actually sequentially generate this on a state. So that was then to the question is like how is there actually a systematic way how we can get then some interesting phase transition in this class of isometric tensor network. And then we found a construction that works, but I'm still struggling to understand how useful this approach is. And the idea is now the following. And so the starting point is now a classical partition function. So we have now a classical partition function which we can write down in terms of a tensor network. So this is just the generalization of maybe how to write down the 1D Ising partition function in terms of transfer matrices. Now we just write this in 2D. So now we have these tensors W, which if we just multiply all or we contract over all of them, we get then the partition function. Now every classical partition function you can turn into a quantum state using this so-called plumbing construction. So, and this is kind of like a standard way of basically transforming now classical partition function into kind of quantum tensors. So we now take these W tensors that we see here that we get from our classical partition function, and now we put here some delta functions on, and we see that now if you're just forming this tensor trace, you're not getting just a number which is a partition function, but then you get the amplitude of a then you just get a superposition of many quantum states. Just to illustrate this a bit more, so if we have now a quantum many-body state where we say that this is now the sum over I1 through IN, then we have psi I1 through IN times whatever basis we have here. Now these amplitudes here are now just given if we just contract all of these tensors. So you see that if we just take our tensor network where we have, say, here our physical degrees of freedom using this tensor notation, then we have here these degrees of freedom I1 through IN, and then this would be the amplitudes that we get in our state. So now we can make the following observation. If we're just using this construction to form our isometric tensor network, if we just use this construction to get our tensors, and we now demand that these tensors in the classical partition function fulfill the rule that if we just turn these tensors into matrices, where we just group like indices, say ij and mn. And if these matrices are now made out of normalized rows or columns, then this automatically turns into a isometric tensor network. Right? So basically we have now like a subset of our partition functions which fulfill this row or column normalization condition, and then these are automatically isometric tensor networks. This is like a strong restriction, and I wasn't really sure about what kind of states I actually sit in, and I still am not really sure what kind of states are in there. But what we found is that we could actually construct a simple, like in this class of the states now, a phase transition between a trivial toric code and an FET toric code with a phase transition in between it. And interestingly, in this class of states, we have now a critical point where we have algebraic correlations in one spatial directions. And let me just quickly maybe comment on this problem, because I think this was not very clear. So if I now think in terms of the toric code model or the 8-vertex model, and I have now my tensors, where I say that these are now these indices ij, mn, and I now turn it into a matrix where I have ij, mn here. Now if I just write down the partition function of the 8-vertex model, then that would look something like this. So basically, these are now, whenever these things that live on the bonds are in a good configuration, so that maybe if all of them are plus, then this is an allowed configuration. If I have 1 minus here, then this is not an allowed configuration, I just get a 0, right? So these are now exactly the 8-vertex configuration that are good. And now I can just normalize this with 1 over square root of 2, and now I see that the partition function of the 8-vertex model is exactly fulfilling this constraint that I have all my rows normalized. And then what we did, like the path that we found, is basically say that, well, now we can also write down a partition function where we actually now allow for negative weights. And now what we are doing is we can then tune basically the parameters. And there's a critical point, and the critical point we have then a 6-vertex model, where these ones here are 0. But now you see that if these ones are 0, now this matrix doesn't fulfill our constraint anymore, because now then these rows are not normalized anymore. But what I can do then is that I can now pick a specific point in the 6-vertex model, which is the one where I then would just put here 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, and 1 over square root of 2. So basically this special point in the phase diagram of the 6-vertex model fulfills this constraint. And this is now exactly the critical point in this language. And this is now exactly the intersection between the rough and the flat phase. So this is basically the ferromagnetic point. Yes?
Is there a simple way of understanding why it's a continuous versus discontinuous transition? Symmetry reason or something?
I don't know.
It's hard.
The thing is, in both sides, it's a disordered space. But the thing which is new, I think, in this is that these are then classical partition functions, but then we have basically like negative signs, negative weights, and this allows us to get it, which in the classical sense doesn't make a lot of sense. But if you think of this as being quantum mechanical wave functions, it does make sense.
But both disordered phase, you might think it's a first order.
They're both disordered, but they are different topological phases. I mean, they just have different, like, so we can, this is a bit involved, so I don't have to deal, but we can write down a sort of membrane order parameter, which is a generalization of string order, which we have for one-dimensional SVT phases, and that changes at this phase position.
All right, but thank you.
Yeah, and on the level of the toric code model you initially explained, so is there a simple version of this where you can dress up the toric code model to get the symmetry enrichment?
Yeah, so the way that we can think about this is it's a bit similar to the toric code, but then we don't have AKLT chains. It's basically more that we have some sort of cluster state model. Because in the cluster state model, you have then a phase transition which is protected just by time reversal symmetry, and this is what it corresponds to. But it's still that the local Hilbert space is 2, not 3, as in the I don't have an as simple picture.
But you can't just add some extra degrees of freedom to the toric code.
No, it's not. It's basically intrinsic. So for this simple example, I would say that, well, I'm going from a 2-dimensional local Hilbert space to a 3-dimensional one, where I would say that I just basically have nothing, or I have a AKLT chain. And this doesn't work here, because here we still have only a 2-dimensional local Hilbert space. I'm not sure I got this across very well, but the reason why the different ways why I'm excited about it, because for a long time I sort of thought it wouldn't be possible to get algebraic correlations with a sequential circuit, and that actually does work for this kind of fine-tuned cases. And then secondly, I still don't really understand this class of classical partition function which fulfill this constraint, what it actually, I mean, what other kind of phase transitions are in there, or is there something interesting about it? Yeah.
So two things. One, it's now 20 minutes of questions.
Okay.
But the question about your comment there about the algebraic correlation. So if you contract this down to your, if you contract this as you normally do with your isotensor network, so you end up, you contract the sides and then you have a 1D contraction to do. Is there something special about the transfer matrix along that allows the, I mean, it is weird that you're getting these algebraic correlations. You don't expect them. If anything's isometric, it's essentially 1D contractions, and the exponential decay is just because you have a transfer matrix that isn't degenerate.
Right. No. But the thing is that if we just do this contraction, so basically we know that it can't be algebraic in multiple directions, but if you just go in one direction, it's perfectly fine to have long range correlations.
And that's along perpendicular to the so your sequential circuit you're constructing this diagonal way progressing through the system. Which direction is the algebraic correlation? It's
like here in the, and there's also a nice kind of picture of how you can understand it. So basically, if you think of these kind of loop constraint, now what you basically, if you draw this picture just in terms of these loops, and you just think about now right. So now we just can tune the boundary, and we have at this point we have this U1 constraint. So now when if you think about a single loop element, that would just do a random walk in this direction because the number of loop segments is conserved. So basically then you would find that this is now would be a random walk. And from this random walk, you get then a 1 over t squared, 1 over the square root of t decay. And this is what we see in these states. Yes.
So related to that, when you draw the random walk analogy, so is there anything known about them with critical theory based on properties of random walks? What is it, some conformal field theories?
There's something known, but I mean I know that I know the scaling that there would be this 1 over like that there would be the decay as 1 over the square root of r in one direction. So this you can basically get from the diffusion equations. Right. But other than that, I don't. So it inherits a lot from diffusion in 1D. So let me now quickly come to the second part, where I want to just now take these kind of toric code states, and which I just previously just mentioned only the entanglement properties, and there I recently learned from this collaboration, which was really driven by Wentao, who is a student in our group, is a postdoc in our group, and Tibor was a student in our group, and my colleague Michael Knapp. And here the idea is that we use higher form symmetries to understand these topologically ordered phases. And let me just maybe quickly go over these slides, and then we can add to a discussion. But I go quickly over it, and then it's up to you if you want to discuss it more. So basically, I mean, what I already kind of showed that we have now these different phases, and on the one hand, we have phases which can be described by spontaneous symmetry breaking. Well, we already discussed these kind of symmetry protected topological aspect where symmetry is important but not broken. And then we have topological order, which so far I just explained it's something where we don't require any microscopic symmetries, and I just entirely talked about this in terms of entanglement properties. But there's now a sort of, I don't know how you would call it, but there's like a different perspective on topological order in terms of so-called higher form symmetries. And what are higher form symmetries? We can have now some sort of p-form symmetry where for our, or in our context, we can think about of a p-form symmetry now being a symmetry operation which acts on a d minus p dimensional manifold. Just for concreteness, so if I just take d equals to 2, so two spatial dimensions, and we have a zero form symmetry, that would be a symmetry that acts now, it's now just a typical global symmetry, which could be just a spin flip symmetry in the Ising model. That would be a zero form symmetry. But now we can also have, for example, a one form symmetry. The one form symmetry would be a symmetry that would maybe just a product of sigma x operators. So that would live on a one-dimensional manifold. So and now it turns out that the topological order, exactly the type of topological order we found in the Tory code model, can actually be reinterpreted as a spontaneous breaking of one-form symmetries. And what basically in this work, this ongoing work, what we basically discussed is now a relation between the entanglement properties of a system and the higher form symmetries. So that, yes?
Sorry, when you say specifically one symmetries, that's not going to imagine 3D, but also two symmetries.
You can, yeah, any p-form symmetry you can think of. But let me just illustrate now
what do you mean by that an operation on one of those loops leaves the energy unchanged?
That's right. And exactly why I want to, just to make, because this was also new to me a few months ago. So I want to just quickly illustrate these ideas for the Tory code, which is very simple. So now we just go back to the Tory code model as we discussed it before, and we realized it on the quantum computer. And this was actually what drove also this project, because now we were interested in kind of different ways of for example, detecting topological order. So now we just take the Tory code model, defined as before, with a slight difference that I exchange x and z, because I want to now match up with the common convention used in lattice gauge theories. So we have the A terms, which are product of x's, and the B plaquette term, which are the products of z's. And now it's not hard to see that this Hamiltonian now commutes with a string of x operators and also with a string of z operators defined in the following way. And these go by name like this of de Hooft loops and Wilson loops. If we now take the ground state of the Tory code and we put it on a non-trivial manifold, for example, a torus, then we find that the ground state wave function actually transforms non-trivially under operations associated to non-contractible loops. This is exactly, so you start from one of the topologically degenerate ground states and you're acting on it with, say, a Wilson loop or a de Hooft loop, and then you just transform it to a different state, which means that this is like the indication of the one-form symmetries actually spontaneously being broken. And now there's something quite, which I find quite striking, is now that the following picture, because we know what topological order is extremely robust. So if we now detune the Hamiltonian, if, for example, we add some longitudinal transverse here to it, we expect the degeneracy to be still robust. It's the topological degeneracy, so it should be robust. And this is now also reflected in this picture of these one-form symmetries, because while these terms break the one-form symmetry at a microscopic level, however, there's still an emergent one-form symmetry. Basically, what we can do is we can now just, instead of considering these kind of thin loops or like these loops, and we can broaden it, we can now have some other operator which will in this low energy space still act as a one-form symmetry. Right? So in this way, these higher form symmetries are different from zero form symmetries, because if we have, for example, symmetry breaking of a zero form symmetry, then if we just break this symmetry immediately, the associated features will go away. Here, however, we find that these higher form symmetries are more robust. Yes?
I have a question, because what exactly does it now mean to be symmetry one-form symmetry? Because now I have the symmetry operation and a manifold on which I do it.
Mm-hmm.
So is it then, I say it is symmetric when I can choose any such manifold, like certain equivalent class of these sub-manifolds? There's an additional degree of freedom.
I mean, my picture that I've gained so far would be that if we just basically project it down to a low energy manifold, that if you just do this, then this still would be a symmetry. Right? So we basically can now just construct a space which is made out of the low energy excitations. And then this would still be a symmetry if you just basically just project the Hamiltonian down to that subspace. Yes.
So, I'm not sure I understand the fuzzy picture in non-zero fields. Is there a way to make these loops as factor operators that actually commute to the Hamiltonian?
Not with the full Hamiltonian, but with the Hamiltonian projected down to the low energy manifold. That is my picture at the moment.
But that it depends on what order of perturbation theory you're allowed.
That's right, yeah.
X and Z to operate. So effectively, I mean, then you're projecting HX and Z out because the system is gapped.
Do we project them out? Because if I mean,
Well,
my picture is more that I'm again. I mean, I'm very happy to have this because I'm still trying to understand it. But the picture that I would probably have is that if you just say that you just start from the toric code state and now you would just adiabatically change, like you just adiabatically transform from turn adiabatically on these fields, that would just give you some unitary. Right, so you just basically have a unitary, like you just do a slow time evolution, and now you have a unitary, which is in a path going from wherever the toric code fixed point was, and then you can now take the original operators and you just transform them under this unitary, which is a finite depth unitary. That I think is that at least in my picture would be the unitary that generates these kind of pattern strings. This is my picture, but I this is something I'm still learning about. But this is the picture that I have. And then if you just basically take these kind of emergent symmetry, which is at a certain energy scale, then it would just have all these kind of properties. Right, and basically, and now maybe I just stop by just giving the overview of what we are currently now working out, and it's basically what we did so far is that we now then just did a tensor network study of this model. So we now have a more general lattice gauge, like a Z2 lattice gauge model for which we do a tensor network study. And first of all, we found that certain cases, for example, the toric code and the Ising gauge Higgs can then be related by an isometry, and that in turn leads to a quantum channel, which allows us that we only have to do variational optimization of the toric code, and we can directly get the entanglement properties of the Ising gauge Higgs. And then we just find that due to the interplay of Gauss law and one-form symmetries, we get some extensive degeneracies in the entanglement spectrum. And also we find that there are some Ising phase transitions in the entanglement Hamiltonian if we just tune the fields in the toric code phase. But yeah, maybe leave it as this, and then there can be questions if there are any.
We have another 5 or 6 minutes for questions. So
I have a philosophical question.
Okay.
For quite some time, myself and I think many in the community argued that phases beyond Landau are cool and solutions beyond Landau. Now we see that this topology over a phase is actually in a way Landau-like, right? It is symmetry breaking, but of some more complicated symmetry. So does it mean that ultimately it's just Landau? Everything is Landau-like?
A good question. No, but this is exactly what got me. I found this paper by John Greavy, which I really like. This is basically what piqued my interest into this. So there exactly having this discussion, and he that opens up the paper saying that, well, we just like to introduce now topological phases as something quite exotic, and we just draw a donut. But then it turns out that it can also be understood in terms of this higher form symmetry breaking, but it has these kind of intrinsic difference, and this is also what the discussion was just about. I mean, we have now, so if we just have standard symmetry breaking, and it's maybe most dramatic, and if we just take a system with a continuous symmetry and break the symmetry explicitly, then, for example, all the Goldstone modes will immediately gap out. So all the features that you have go away the moment that you just remove the symmetry at the microscopic level. And the thing which I find very exciting about these higher form symmetries is that now the features remain robust, even if you just tune away, and that's still very special. And so it's maybe just a different way of formulating this topological order, which this is one comment, and the other comment, and this is again, I can't prove the following statement, but this is what I at least understood from literature that I read, is that this construction works for a certain set of topological phases. As I understand, if you take non-Euclidean topological orders, there is, at least it's not known to me how to phrase it in terms of higher form symmetries. But again, this is something which I'm still in the process of learning. I don't know if this answers your philosophical question.
Any other questions? Philosophical or not?
So what is it about zero form symmetries that sort of distinguishes them? If all these people symmetries have this like ability to be more stable in a sense, like why are
Well, the zero form symmetries would not have it, right? So
yeah, why are they different from all other people?
my picture would be that if you have a zero form symmetry, then there's no way that you can, there's no extra dimension that you can make it transform it to a fatter string. I don't know, this is at an intuitive level, this is how I would think it, that there is basically a way that you can adiabatically transform it to something that is still conserved in this low energy manifold, while this can't be done for zero form symmetries.
I have a very simple question, I think, just to check out. So is a D-form symmetry then a gauge symmetry in this?
That would, yeah, that would be like a
So
local
this takes
symmetry.
us from sort of global symmetries to gauge symmetries through these different higher form symmetries.
I think so. At least this is if you follow down this, yes. But I again, there's lots of interesting literature, and there's also like several old papers, even by Zohar Nusinov, he does look into this very early on, and there's some also some paper by Zyberg, which I'm still trying to digest. I mean, maybe this has been discussed in literature, but I don't.
So your statement seems to be that a P-form symmetry can be understood as a zero form symmetry on a reduced space, and the reduced space happens to be zero dimensional for a gauge symmetry. Is that?
That's what I understand here.
Sorry. Question. Oh, was there a question somewhere else?
Question is, can the lens projector symmetry be used to constrain the possible P-form symmetries in a particular, for example, Symmetries state?
I cannot say it's a good question. I don't know the answer. I mean, no, I haven't thought about this connection.
This may be an overlapping question with Andrew's, which is, of course, we know we have various phase transitions in gauge theory models, but we also don't have a well-defined order parameter. Do you think this could give any complementary?
There will be the hope, yeah. Because like now also, this is not part of this talk, but this is also what we are now thinking about, because now there is some like one type of order parameter for these gauge theories are these Friedhan-Marcoux type order parameters.
I don't know. What does that mean? Does that mean a string order parameter between two sites?
Exactly. So it's basically like again we can explain it also for the toric code model, right? If we take exactly this model, and now we can write down an operator which indeed is just a string of x's, for example, and now we can calculate the expectation value of that operator. Now in the toric code phase, this operator will create now two anionic excitations at its end. So the expectation value is 0. If now you just tune the x field and you go to x being infinitely large, then the field is when the state is that x polarized, and if you're now calculating this expectation value, that expectation value will be 1. And now if you look at this Hamiltonian and you just only tune this field, now you find that this x string, if you just do it on an infinite loop, or like if you just do it on a closed loop or infinitely long, then this is actually a symmetry of the Hamiltonian. And then it basically is the same idea of having the string order in one-dimensional systems. I can. the way that you think of string order, for example, for the AKLT, is that you just take a. So if you just take an AKLT chain, and now you just look at the standard kind of string order, what it corresponds to is that you just apply basically you have an expectation value of just an operator which would be just the symmetry, like some pi rotations about SZ, for example. And that would be a string order. And of course, depending on which kind of operator you just terminated with, it's either zero or non-zero in the AKLT phase. And the reason why this works is that if you just start from the ground state, then it creates something that is charged at the boundary or not. And this is the way how the string order works for SVT phases. And basically this FM order parameter is now something similar for these topologically ordered phases, but in these kind of fine-tuned cases that would then this symmetry operation corresponds then to a one-form symmetry. So there is some connection, and then
I think with that, we should drink coffee. Time to chat. We resume that, what time do we reach the hour? 20 to the hour, okay.